This lesson is on second derivatives and graphs and how everything is related. So the first thing that we want to talk about here, we're just going to take a regular graph and we'll make sure you know some terminology. So if I just have this sketch, there's a special point right here which I'm going to talk about in just a second. You need to remember what it means to be concave. Okay, and we're used to parabolas. For example, a parabola that's face down, that is concave down. And face up would be concave up. But not every graph is like a parabola where it's always concave down or always concave up. So this graph that I have sketched over here, the first part of it is kind of curved down, caving downward like an upside down U, but it doesn't quite make it all the way. That part of the graph is concave down. And then the second part of the graph where it's kind of upward, it's almost U-shaped upward, but it doesn't have both sides, obviously. This is considered concave up. Now, when you have a graph that changes from concave down to concave up or concave up to concave down, there's a special point in the middle that doesn't fall into either category. It's like the point where it changes, and that is called a point of inflection. And so you need to know that terminology to be able to talk about the other things that we're going to be talking about today with derivative graphs. Okay, now we're going to write relationships in this chart that we know. And we learned about the derivative graph in our previous video. And so where the original was increasing, you know that the derivative was positive. And I'm just going to write plus. I'm not going to write the word out. Where the original was decreasing, the derivative was negative. And then where the original had a critical point, the derivative was 0. Okay, and again, we're going to expand on those critical points later. For right now, we're saying 0. Now, what we're adding to that today is concave up, concave down, and points of inflection. So this is new to you. If the original is concave up, the second derivative is positive. If the original is concave down, the second derivative is negative. And if the original has a point of inflection, the second derivative has a 0. So it has a really similar relationship. It's just with these other three characteristics of a graph. So derivative can tell us about increasing, decreasing, and critical points. Second derivative can tell us about concavity. Now, what happens is there's also a special relationship with these three and the derivative graph, because the second derivative is the derivative of the derivative. So if the second derivative is positive, that means that the first derivative was increasing, because they have that same relationship as the original and the derivative have. If the second derivative is negative, the original is decreasing. The first derivative is decreasing. And if the second derivative is 0, again, the first derivative is going to have a critical point. And again, that is because they have that same relationship with the first and second derivative as you have with the original and the regular derivative. Now, this part over here that we didn't put anything in, for a reason. You can't actually figure anything out there. So we just have to know these relationships here and how they're related. Now, what most of the time is going to happen, and I'm going to say like 90% of the time, they give you a graph or knowledge of some sort about the derivative and ask you about the original. So if you think about it, just looking at the derivative, you can answer all of these questions over here, these 6 questions. So if you're looking at the derivative and they ask you where the original is concave up, you look where the derivative is increasing. If you're looking at the derivative and asked where the original has a point of inflection, You look for critical points on the derivative. So again, that relationship is very important to know and remember, understand, memorize something, but you need to get this. Okay, we're going to take this example, this parabola, and we're going to say that that is our original. We are going to sketch the derivative and sketch the second derivative, trying to know everything that we can about those sketches. So, the first thing that I'm going to do is what we had been doing before. And where f is increasing, I know that my derivative is positive. And so my derivative is positive until I get to 2. And then where f is decreasing, I know that my derivative is negative. So I am negative after 2. And again, notice I'm making that relationship be quadratic and linear because I know how the algebra of derivatives work. So I should go from an x squared to an x power. Now, you can get to the second derivative 2 different ways. You can look at the original and say, well, the original is concave down everywhere, so the second derivative has to be negative everywhere. So everything that I draw is going to be below the x-axis. Or I can also think, okay, this derivative of the derivative means that since this one is decreasing, we are negative everywhere. Because it's linear, if I knew more about it, I could get the actual number because it would be the same slope everywhere. The line, or the derivative, second derivative, would be a horizontal line because every y value here would be from the slope of this line, which is the same everywhere. And so again, we are going down in power from something that is y equals x squared to something that is y equals x to something that is y equals a number graphically. Okay, but again, I could get to that negativity by either looking at this as concave down or looking at this as decreasing everywhere. Okay, again, we are going to look at graph 2 and do the same thing. We're going to look at graph 2 as being the original. I'm going to sketch the graph of the derivative, and then I'm going to sketch the graph of the second derivative. So, on the original, again, I'm going to look at increasing and decreasing parts first. It is decreasing until about a half or so. So I should be negative before that. It is increasing from that about a half to about 1.5. So I should be positive. And then it is decreasing from there on, so I should be negative. Now that is a general sketch, and it probably should look more like a parabola of our derivative. I can get a little more specific now that I know about this second derivative because I know that there has to be a max right in here. Where would that max occur? A max on the derivative is a critical point on the derivative. And if you look back at our table, where the derivative has a critical point, the second derivative was 0, or the original had a point of inflection. So since we're looking at the original graph, if I find a point of inflection, then I'll know that's exactly where that max should be at. So going back to the original, we were concave up and then concave down, and it looked like it changed about right here at 1. So I know that this max, the top of that hill, should be perfectly at 1. So if I wanted to redraw my sketch and make it a little nicer, I know that, again, I should be crossing at about a half. I want to make that max at 1 and then cross at 1.5. So you can get a little more specific now that you know about the second derivative. Okay, the next thing that we want to do is draw the second derivative. And again, you can look at the original and the concavity. The fact that the original is concave up before 1 and concave down after 1 tells us that this graph of the second derivative is going to be positive and then negative. Okay. You can also look at the derivative and see that it was increasing and then decreasing. So again, you're positive before 1 and negative after 1. And again, it follows the powers. Here you've got a negative x cubed, here you've got a negative x squared, here you've got a negative x power. Okay, we're going to approach 3 just slightly differently. We're going to do the same thing. This is the graph of f. I'm going to sketch the graph of f prime. Okay, and then I'm going to, well, we're not going to approach this one quite differently, sorry. If I had the derivative graph, I would. Sorry, and then f double prime down here. We'll just go about this the same way. So again, when I'm drawing the graph of the derivative, it's just like before. I'm looking at where the original is increasing and decreasing. So the original is increasing before negative 3. That means our derivative is positive before that. It's decreasing from negative 3 to negative 1. That means our derivative is negative. It's increasing from negative 1 to 2. So I should be positive on my derivative. And I'm decreasing from 2 to 4. So negative derivative. And then increasing from 4 on, so positive. And again, that makes sense if it's polynomial, because this is a fifth, this is a fourth. Now, for the second derivative, again, I can look at this and say, okay, it was concave down, then concave up, then concave down, then concave up. So I should be negative, positive, negative, positive. Again, if we look at the points of inflection on the original, I can find those maxes and mins here, and there's zeros here. So I'm going to kind of do that, let me do that in a different color. If you're looking at the original graph, it looks concave down until about right here, which I'm going to say is negative 2, even though it's not exactly, but we'll say it's negative 2. That means that you have a minimum at negative 2 on the derivative graph, and you have a 0 at negative 2 on the second derivative graph. Then it looks concave up until you get to about right here, which is about maybe a half. And so this max is technically at a half, and I'm going to cross the graph of the second derivative at a half. Then on the original, I'm concave down until I get to about 3, and then I change to concave up. So because it changes concavity at 3, I'll have a minimum at 3 on my derivative, and a 0 at 3 on my second derivative. So these 3 points of inflections were maxes or mins on the derivative, and they were zeros on the second derivative. Now I can look at my original graph again and say, well, concave down meant that my second derivative was negative. Concave up meant that my second derivative was positive. Concave down meant that it was negative. And concave up meant that it was positive. I can look at it that way, or I can look at the way I've been doing. The derivative was decreasing, so the second derivative is negative. The derivative was increasing, so the second derivative was positive. The derivative was decreasing, so the second derivative was negative, and then the derivative was increasing, so the second derivative was positive. The relationship's there whichever way you look at it, but it might be smart to find those points of inflection first. Okay, 4 is just a line, so I want you to try to pause and draw the derivative and the second derivative on your own. Okay, so number 4, you're looking at the original graph. It's a line, so it's a little bit easier than the ones that we've been doing. Since the slope is negative, you expect your derivative graph to be completely negative, so completely below the x-axis. And you can actually figure out that that is negative 2/3 by calculating the slope. And so I'm just going to put a point and say that's negative 2/3. And so your derivative graph would be a horizontal line at negative 2/3, because this line of the original has the same slope everywhere. Now your second derivative graph would be the slope of this line, and what is the slope of this line? 0. So it would be that everywhere, so you have a horizontal line at 0. So this is a case that's been a little different than the ones that we looked at before. But it's like one of the most basic cases that you would have. Now, instead of drawing, we want to answer questions. Like I've told you before, most of the time they're going to give you a derivative graph. So we're going to assume that this is the derivative that we are looking at. And we are going to answer all of these questions about the original graph. So they're asking where the graph of f does these things, but we're looking at the derivative graph. So when I'm looking at a derivative graph and I want to find where the original has a minimum, what am I looking for? I'm looking for a change from negative to positive, which happens at -3. We change from negative to positive, and it happens again at 4. You change from negative to positive. So the original is going to have a minimum at -3 and +4. When you're looking at the derivative trying to find where the original has a maximum, you look for a change from positive to negative. That happens at -1 and only -1. At 2, granted it is a 0, but it doesn't change, so that would be a flat place on the original, although I'm not asking that right now. Alright, part C, we are asking where the original is increasing, so what do you look for? You look for where your derivative is positive. Derivative is positive where the original is increasing, so between -3 and -1, and after 4. Decreasing would be where the derivative is negative, and so there's 2 sections here that are negative. We have one from -1 to 2, and we have one from 2 to 4. You can't include the 2 because we've established that's a flat place. Then, here comes the new question. Where is the original concave up? Well, if you go back to that table, the original is going to be concave up where the derivative is increasing. So the derivative is increasing until about -2. So -infinity to -2. It's also increasing from about 0 to 2 and from about 3.5 on. So again, where the original is concave up, the derivative is increasing. So I just list all of the increasing sections. And then where the derivative is, where the original is concave down, the derivative is decreasing. So I'm listing the decreasing sections, so from -2 to 0, from 2 to 3.5. And then the last thing is points of inflection. Points of inflection on the original are where the derivative has maxes or mins. So this one has a max at -2. It has a min at 0. It has a max at 2 and a min at 3.5. So your job is to learn these relationships to be able to answer questions like this. So move on to number 6, and I'm going to pause and let you answer those questions, those same questions about this graph. Okay, so if you've done it correctly, you should have a minimum at -7 because the graph changes, the derivative graph changes from negative to positive. You should have a maximum at 5 because the derivative graph changes from positive to negative. The original should be increasing from -7 to -2 and from -2 to 5 because that's where the derivative is positive. The original is decreasing before -7 and after 5 because that's where the derivative is negative. Now the new ones, we're looking for the original to be concave up where the derivative is increasing. So that would be -infinity to about -5.5 and from -2 to 3. The original will be concave down where the derivative is decreasing. So from about -5.5 to -2 and from 3 to infinity. And then the original will have points of inflection where the derivative has maxes or mins. So about -5.5, -2, and 3. Okay, and the last one, again, it's time for you to pause and try it on your own. Okay, so your answers for that last graph, we should have a minimum at 0 because the derivative changes from negative to positive, a maximum at negative 2 and positive 2 because the derivative changes from positive to negative at those places. The original should be increasing between negative infinity and negative 2 and 0 and 2 because that's where the derivative is positive. It should be decreasing where the derivative is negative, so that would be negative 2 to 0 and from 2 to infinity. It should be concave up where the derivative is increasing, so that would be from negative 1 to 1. And it should be concave down where the derivative is decreasing, so that should be negative infinity to negative 1 and 1 to infinity. And then it will have points of inflection where the derivative has maxes or mins, so that's negative 1 and positive 1. And hopefully you're taking this in, and that concludes this lesson.